All right, this video is going to review some geo and some trigonometry of three-dimensional solids for the IB Math Studies exam. I'm going to have my calculator open in case we need it, and I might go kind of fast. I'd like to cover a few different examples so you can see what you might get asked. I'm starting with a basic trig question. It doesn't ask us to use any of the formulas for volume or surface area, so we're going to go over those formulas after we cover this example. This is just an application of things like Pythagorean theorem and sine, cosine, and tangent, right triangle trigonometry, but in a three-dimensional figure. So it tells us that we have a square-based pyramid, so I know that all the corners in that base are going to be 90-degree angles. The sides are all 4 centimeters, as it says in the question. So I can label, 4 centimeters here, 4 centimeters from A to B, B to C, O to C. The vertex, D, is 3 centimeters directly above X. So if I wanted to label that, I can put my 3 there. X is the center of the square, M is the midpoint of AB. So this is the information that we have to use going forward. First, it asks us to find the length of XM. There's not really much calculation to do here, which is why the instructions are fine. X to M would be half the distance across one of the sides of that base. So if, like, from O to A was 4, then half of that is going to be 2. That's going to be the same distance as it is from X to M. So XM is going to be 2 centimeters. Next part is to calculate the length of DM. The length of DM would go from the apex of the pyramid down to the center of one of the sides. And to calculate that, we can use the right triangle that we have drawn with the red, blue, and the green line. Get rid of this blue line here. Knowing that there's a right angle here because it's a right pyramid. To figure out the length of DM, that's the hypotenuse. We know that the height of this is 2. We know from X to, the height is 3 rather, from X to N is 2. So we can just use Pythagorean theorem. 3 squared plus 2 squared equals dm squared. And we'll solve this on the calculator. So 3 squared plus 2 squared. We're going to square root that answer. I know the square root of 13 would be simplest radical form, but we're going to give our answer to 3 significant figures. So 3.61 would be dm. We want to show our working there, just in case we were to make a careless mistake. The units are centimeters. So we could still get some partial credit for having the correct formula filled in the Pythagorean theorem. And now it asks us to calculate the angle between the face ABD, which is that triangle over here, so this whole face, and the base of this pyramid, which is the rectangle OABC, or the square OABC. So to figure out the angle between that face and the base, it's really asking us to find this angle right here, because DM is on the side face, and XM is on the base. So if we have a line that is on the side face and a line that is on the bottom face, and we're trying to find the angle between them, we can just find the angle between those two lines. And so I'm going to use the tangent with the 3 and the 2, opposite over adjacent. And then inverse tangent if you're trying to find an angle. Just make sure that your calculator is in degree mode before you do any trig calculations. Let's see, inverse tangent, 3 over 2. 56.3 degrees, giving it to 3 significant figures because it doesn't say otherwise. Okay, so there's a basic trig question in a three-dimensional figure. Now let's review these formulas that are going to be given to you on the formula booklet. So the formulas given to you are all about either surface area or volume. Notice how few of them are about surface area. Where I draw that green line, the ones above it are about surface area. All of the other ones are about volume. The reason being, they expect you to figure out a lot of the surface area on your own, sort of using common sense. If you have something like a pyramid or a cuboid, which is a bunch of rectangles, they expect you to be able to figure out the surface area of that just using your geometry skills. So notice the areas given are only the curved surface of a cylinder, the surface area of a sphere, and the curved surface of a cone. They're not giving us any surface area formulas for those triangular three-dimensional shapes or rectangular ones. So they expect you to know how to get area of a triangle and area of a rectangle, and then put those pieces together if you have a shape with those on the side. So hopefully we'll get to an example that has one of those so you can see what I'm talking about. The confusing thing I want to go over with these area formulas, when it says, for the very first thing on this list, the area of the curved surface of a cylinder, you can picture that a cylinder has a circular top, a circular bottom, and then if you picture it like a can of tomato soup, where you would put the label around here and all around the other side as well, that's the curved surface. So it doesn't include the circle at the top and the circle at the bottom. So when it asks, or when it gives you that area equals 2 pi r h, that's only the area of the part around the side of the cylinder. It does not include the top and the bottom. And they don't give you the top and the bottom anywhere on this list. That's because they expect you to know the top of the cylinder is just a circle, and a circle is pi r squared. So if you're trying to get the area of maybe a trash can, you have to just know the top is not going to include a circle, the bottom will include a circle. And so you'll be doing this formula, the curved surface of the cylinder, plus one circle. If it was a can and they actually wanted you to get the entire surface area of the whole can, maybe how much metal is going to be used to produce it, then you're going to want to do the curved surface, also a circle at the top, also a circle at the bottom. So you have to do some thinking to know which of these formulas to apply and what to apply from outside of this list, like circles, like triangles, like rectangles. It doesn't have those areas included. For the surface area of a sphere, that's the next thing on this list, there's no trick to that. The formula here is giving you the surface area of the entire sphere. That's how I like to draw a sphere. So front, back, top, all around the surface area of the whole sphere. Just know that often you won't have to do an entire sphere. You're going to have something like half of a sphere called a hemisphere. And they're not going to give you that formula. You have to know that that's just going to be a sphere divided by 2. If you have a hemisphere, where you're actually, let's say you have this figure given to you, right? It's a hemisphere, and you're asked to find the surface area of it, including the bottom. So if you can picture this as like an upside-down bowl, for example. If it's an upside-down bowl, then that bottom will not be included because it would just be an open circle. But if this was a figure where you were actually asked to calculate the entire surface area, including the curved part and the circular bottom, you'll have to know that it's going to be half of this formula plus the additional circle that is now there on the bottom. So when you cut a sphere in half, you get that circular bottom that would be kind of resting on the table if you had this figure resting on a table. So you're going to have to do some serious thinking when you're asked to do area calculations. And then the final area formula to go over is the curved surface of a cone. So you know a cone has a circular bottom, rises to an apex. The curved surface is only all of this, and it doesn't include the circle at the bottom. So if you are doing a surface area of an entire cone, including the curved surface and the bottom, you have to add a pi r squared to the formula that's given here. This formula is only for the curved part. Okay, and then all of the volume formulas are fairly straightforward. So let's go ahead and see some examples of these. Here we have an observatory. I look at the figure before I even read the question. I see I have a hemisphere and I have a cylinder. So it's two different figures put together here to give us this observatory. The height of the cylinder is 12, the radius is 15. That 15 is the radius of both the cylinder and the hemisphere. I hope that's pretty clear. First thing it asks us to calculate is the volume of the observatory. Volume is easier. Almost always, volume is going to be the easier calculations that they're asking you to perform because the formulas are very straightforward. So the volume of this observatory is going to include this, everything inside of this cylinder, and everything inside of this hemisphere. So we're just going to have to go to our formula page and find a volume for a cylinder and a volume for a sphere, and then cut that sphere in half to get a hemisphere. There's no trick about extra circles and all that stuff when it's just volume, because volume is just the space inside. So let's pull our volume formula for a cylinder. Erase all the markings that I put on here. Volume for a cylinder is going to be pi r squared h. And volume for a sphere is 4/3 pi r cubed. And just know you're going to have to be doing half of that. So pi r squared h, volume is going to equal pi r squared h, that's for the cylinder, plus 4/3 pi r cubed, that would be for the sphere, but just know that you're only taking half of it because we have a hemisphere. If you show that formula correctly, you can get some points just for having that formula written, right? And now let's fill it in with the correct information. So the volume is going to equal pi times the radius squared times the height. I paid attention to make sure that those are in the same unit. They are both in meters, so no tricks there. 1/2 times 4/3 is 4/6. So 2/3 times pi times the radius again cubed. So again, you can get another point for having it filled in correctly, substituted correctly. And then we go to our calculator and evaluate this thing. So we have pi multiplied by 15 squared multiplied by 12. Let me pick up the multiplication. It did. Okay. Plus 2/3 multiplied by pi again, multiplied by 15 to the 3rd power. And I'm going to hit Control-Enter so I can get this as a decimal to 3 figures. 15550.9. That's more than enough significant figures. Yes, you need to put the correct units on volume probably in order to get full credit for the question. It's cubed for volume, so meters to the 3rd power. Then the second part of this question tells us the hemispherical roof is to be painted. If you're painting the roof of this, that's only on the exterior. It is not going to include this circle here. We are just painting the outside of the hemisphere, right? The whole outside of the hemisphere. Sorry, I'm trying to picture that. So where all that green is shown, you're painting the outside of the hemisphere. Calculate the area that is to be painted. This is a very straightforward question. We're going to take our surface area for a sphere formula and simply cut it in half. So 4 pi r squared. So surface area is going to equal 4 pi r squared. It's going to be a whole sphere. We're going to cut that in half. Cutting the hemisphere. Plug in our radius. Perform this calculation. 2 multiplied by pi multiplied by 15 squared. It's giving my answer in scientific notation. That's fine. I can calculate with that. Oh, that's a mistake. It accidentally took my answer from my previous question and tried to involve that. I wanted to do 2 multiplied by pi multiplied by 15 squared. Let's try that again. Much better answer. Okay. Thought that area seemed far too large. 1,413 units on this one are going to be meters squared. This is a surface area question. Area is a squared unit. This is actually a very simple question. I just wanted to show it because what they often do with these three-dimensional questions is bring something else in, some other math that you're supposed to know. For example, in this one, part A asks us to just calculate the volume of a cuboid. And it gives us the 3 dimensions. So you just should know a cuboid, in case you're not familiar with the word. A cuboid is a rectangular prism, right? It's rectangles on all sides. The top and the bottom are going to be the same. Could be a square, could be not a square. To get the volume of a cuboid, you just multiply length times width times height. I believe that's even given to you on the formula booklet. Let's check. Yep, volume equals length times width times height. So to get the volume of this cuboid of part A, we're going to do 16 multiplied by 1 3/4 multiplied by 2 2/3. 16 multiplied by 1 3/4 multiplied by 2 2/3. I think I'm going to enter this as 8/3. That's the same as 2 2/3. And it is 74.7, around 3 significant figures. The units on volume are cubed. And then the next part asks you to apply some estimation, some percent error. Jim estimates the dimensions of the container are 15, 2, and 3, so he's rounding the measurements. Uses those to estimate the volume of the container. So what would his estimated volume be? 15 multiplied by 2 multiplied by 3. 90. His estimate for the volume is 90 meters cubed. The percent error in his estimated volume, just to review this formula, while it is given on the formula booklet, often people feel confident with it, think that they know it, and then apply it wrong. So if in doubt, use that formula booklet. I'm not going to flip back to it now. I will just show you to find the percent error, we want to subtract. Because it's in absolute value, it doesn't really matter which order we subtract it in. The estimate minus the actual minus the estimate. What does matter is that it's divided by actual. We were trying to find it as a percent of the correct answer, not as a percent of your estimate. Multiply by 100 to turn it into a percent. $74.7 minus 90. Divide it by 74.7. And multiply by 100. Multiply by 100. Ignoring the negative because it's absolute value and u is off by quite a bit. 20.5% error. And then the final example I want to go over with you here is a pretty complicated one. This is a paper 2 type question. It involves, some three-dimensional stuff and then some other stuff that they're trying to bring in. So we have a solid sculpture consisting of a hemisphere and a right circular cone on top of that. Show that the volume of the hemisphere would be 18 pi. Show that the volume of the hemisphere. So for part A, we need to use our volume of a sphere formula, which we looked at previously, and I remember is 4/3 pi r cubed. Because it's a hemisphere, we'll be dividing this by 2 or multiplying it by a half. Actually, it looks a little bit nicer. That's how I showed it before, and that's how I'll show it again. And we're plugging in 3 as our radius. Notice I am ignoring the 18 pi that they said the answer is going to be. When it's a show that question, I ignore the answer they give me. I try to find it on my own, show that by doing the working, I obtain the answer that they are also obtaining. Okay, so we want to say 1/2 times 4/3 multiplied by pi. Oh, we'll leave the pi out of it because the answer was given in terms of pi anyway. So times 3 to the 3rd power, which comes out to 18. So this does equal 18 pi. Units are centimeters cubed. So there's the volume of the hemisphere. Then it goes on to say the volume of the hemisphere is 2/3 that of the cone, which means that the cone is actually larger in volume, right? The hemisphere is 2/3 of the volume of the cone. Let's see if we can find the vertical height of the cone. So the vertical height of the cone is this. In order to find that height, we're going to need some information, but we have enough information. We have to figure out what the volume of the cone is first. I know that because they told me in this sentence some information on the volume of the cone, and so I assume that I need to use that going forward. The fact that the volume of the hemisphere is 2/3 that of the cone, you can think of 18. Let's see, you can think of 18 pi. This is just how I think of it. As 9 pi plus 9 pi. That would be like breaking it into 2 even pieces, which means that the cone, because it's larger by 1/3, is going to be an additional 9 pi. So the volume of the cone is going to be 27 pi centimeters cubed, because the cone, right, is larger than the hemisphere. The hemisphere is 2/3 of the cone. So if you wanted to not think about it mental math like that, the way you could do it would be to say 18 pi over x equals 2 over 3, right? Because what we know is that the numerators of both of these fractions would represent the volume of the hemisphere, the denominator would represent the volume of the cone. If you do the same as proportion, what you see is that 3 times 18 is going to be 54, kind of cross multiplying here. 2 times x, divide both sides by 2, and half of 54. It's 27. So 27 pi equal x. However you obtain it, now we know that the volume of the cone is 27 pi, and we're asked to calculate the vertical height of the cone. So we're going to want to use our volume formula for cone. Going back to my formula sheet, volume of the cone is 1/3 pi r squared h. Okay, volume of the cone is 1/3 pi r squared h. I know that the volume here came out to 27 pi. I know that the radius was 3. And I'm going to solve this equation for the height. The pi's will cancel each other out here. Multiply both sides by 3, right? 3 times 27 is going to be 81. 81 equals 3 to the second power, 9 equals h. So the height of the cone, the vertical height of the cone is going to be 9, let's see what are the units, centimeters. Okay, 9 centimeters. Calculate the slant height of the cone. For that, I'm going to use Pythagorean theorem. So this is 9. Using my 9 and my 3, I'm going to calculate the slant height of the cone. So 9 squared plus 3 squared equals the slant height squared. 9 squared plus 3 squared. Square root that answer. Square root of 90 is approximately 9.49. Okay, there's my answer to C. Calculate the angle between the slanting side of the cone and the flat face of the hemisphere. So that would be the angle between the slant height that we just found and where the 3 centimeter radius is labeled. So I can use, sine, cosine, or tangent to find that. I'll use tangent. I want to use the whole numbers. So the tangent of that theta I'm trying to find will be opposite over adjacent. So I'll be doing inverse tangent of 9 over 3. Sorry, I'm kind of all over the page here, but this is making sense. I'm trying to minimize the scrolling that I have to do around the page. Go to tangent, 9 divided by 3. Angle comes out to 71.6 degrees. All right, here's my answer to part D. Right, so this is my answer to B, my answer to C, my answer to D. If you remember, my answer for A was this whole thing. Part A is actually asking us to show some working. Then the final part says the sculpture is made of material that weighs 10.8 grams per centimeter cubed. Calculate the weight of the sculpture, giving your answer in kilograms. If it's 10.8 grams per centimeter cubed, we better figure out how many centimeters cubed this whole thing is. Centimeters cubed is a volume calculation. We already know the volume of the hemisphere, and we figured out the volume of the cone at one point, so we need to put them together. We have an 18 pi for a hemisphere, we have set 27 pi for the cone, so adding together 18 pi plus 27 pi, and this time I'm actually going to involve the pi. 18 plus 27 is 45 multiplied by pi. Get this to a decimal answer, so 141 approximately 372 is how many centimeters cubed this thing is altogether, right? And it weighs 10.8 per each one of those, so I can multiply this by 10.8 grams. Multiply by 108, my mistake. Go back and redo that. Multiply by 10.8. And it comes out to, I'll write my answer up here so that it's all on the screen, 1,526.8 grams, asking us to give the answer in kilograms, so I'm going to have to divide that by 1,000. And it's 1.53 kilograms. So corrected 3 significant figures in the correct unit. And that is my answer to part E. So sorry this one was all over the page. I hope each piece of it sort of made sense. And that's a very thorough review of three-dimensional geometry and trig, as you might see it on the exam. That is it.